Hello and welcome to Nuclear Physics. In this course, we're going to represent different things. We're going to cover multiple subjects starting from the structure of the atom, from molecular structure, the nucleus, different particles constructing the atom, different reactions like nuclear reactions. We state from them beta decay, alpha decay, different types of decays, gamma decay, fission reaction, fusion reaction, etc. And also we're going to get a little bit into subatomic science, subatomic particles. So let's get started. So nuclear physics is actually the study of the structure of the atom. What is an atom made of? At first, in general, or like on a microscopic level, if we can say that, for the atom, we have a nucleus formed of protons, which are positively charged particles within the nucleus. They define also the atomic number, which is Z. So when you see the atom or the naming for the atom, the lower number is the atomic number or the number of protons defined by Z. Also, within the nucleus, you have the neutrons. They are neutrally charged particles, which are slightly a little bit heavier than the protons, also residing in the nucleus, and they act as isolating particles between the positively charged protons, preventing them from, repelling against each other or flying away. Otherwise, because since they are charged the same way or positively, without the neutrons, they will pull against each other, erupting the nucleus. So the neutrons basically keep the nucleus intact. Protons and neutrons together form the nucleon, which forms the core of the atom or the nucleus. As you see here in this graph, in this picture, the protons are, as we mentioned, the positively charged particles surrounded also by neutrons within the nucleus. They form the nucleus, and electrons are the negatively charged particles which are in rotation, in orbit, not exactly circular, but they travel through an orbit around the nucleus. The total charge of an atom is determined by the number of protons, which is Z, positively charged particles, and another definition is atomic number, okay, which is Z. So this is what determines the total charge of the atom. For example, for nitrogen N, the atomic number is Z equal 7, and it is a unique identifier for that element. Now, of course, for different atoms that are at equilibrium, you would see that you would have the total charges of the atom would be neutral, okay, because the protons are negated by the electrons. But we're talking here about the atomic number, which is the number of protons defining, if you will, the positive charge of the atom. As for the electrons, they are the negative charges having a very much lower weight than the protons. And unlike the protons located in the nucleus, electrons travel in a pseudo-random, almost chaotic trajectory or trajectories around the nucleus made of protons and neutrons, and they are not located within the core of the atom. They actually are located around the core, around the nucleus. For an atom, which is in an electrical equilibrium or neutral charge, the number of protons is equal to that of the electrons. If the atom is neutral, it doesn't have a specific charge that is, overriding the opposite charge that is dominant. The positive charges and negative charges of the protons and electrons respectively cancel each other. That's why you get an atom or an element in an equilibrium or electrical equilibrium state. But when the atom loses or gains an electron or a proton, it becomes ionized. Okay, this is N here, not N. It becomes ionized, in other words, charged positively if it loses an electron or negatively if it loses a proton. So this is what it means when we call a gas element ionized, meaning that it has a new charged state after losing one of its charged particles, whether protons or electrons. Now, another variable for the atom is the mass of the nucleus. It is approximately the sum of masses of the protons and neutrons, but the mass of the atom, however, is different because of the energy liaisons holding the nucleus together. Okay? The mass of a nucleon is about 1 atomic mass unit, which is 1.67 times 10 to the power minus 27 kilograms. By the way, by nucleon, we're referring to either a proton or a neutron. The nucleus is this clump of protons and neutrons. Each of them or any of them is called or can be called a nucleon. Now, the mass number of the atom is the number of protons plus number of neutrons. So let's back up a little bit. You see, for instance, the carbon C612. What does it have? The lower number is always the number of protons, which is also designated by the atomic number Z, where P equals 6, P being the protons. And this is the unique identifier of carbons. So any carbon element should always have the same atomic number Z. Now, for the mass number, which is the upper value, it's actually the sum of the protons and neutrons together. Now, this can change from one carbon isotope to another. By the way, different carbon elements or the same carbon element with different mass number we call isotope. But it is still the same element, the same atom type, okay? The same substance, if you will, but with different mass numbers. But when you change the atomic number below, you get a completely different substance. So you go from carbon to nitrogen to something else, for example. Atomic variance, here we go back to stating or talking about the isotopes. So, what is an isotope? The isotope, actually, of an element is a different variant having the same atomic number Z, or the same number of protons, but different number of neutrons. So it has the same chemical properties, but a different mass, okay? The same positive charge, but a different mass. Because the mass number, the upper value, like we saw in C, is different. So isotopes can either be stable or unstable. Unstable means radioactive. It has a tendency to decay. It has a tendency to have a particle break out or break off from its nucleus or from its surrounding trajectories, meaning an electron being released. So, for instance, you have the uranium-235, which decays over time, releasing radiation. Okay. Now, another example, you have plutonium-239. We're talking about the mass number. 240 all the way to 142 are different isotopes for the same plutonium element, and they are tweaked or altered for different scientific applications. Actually, like you have a human hand in these different plutonium versions, okay, and it's not innate in nature. So for instance, Pu-238 is made for space exploration. You have the number of neutrons is 146. Pu-239 nuclear weapons, okay, so it's kind of an enriched plutonium having 145 neutrons. The atomic mass is the weighted average, by definition. It is the weighted average of masses of every occurring isotope for an element, okay, expressed in AMU or atomic mass unit, which we're going to observe later. Now, another atomic variant or definition is the isobars. Now, isobars or an isobar, it is a nuclei with the same mass number A, however, with different atomic number, Z, or the number of protons. In other words, they are a completely different element, but happens to have the same mass number A. So, as an example, you have calcium and argon. They are completely different, two different atoms, two different substances in nature. However, since they happen to have the same mass number, they are called isobar. So, For calcium 40, you have 20 protons, 20 neutrons, mass number equal 40. But for argon, as you notice, you have 18 protons, so it is a completely different element. However, kind of has also 22 neutrons that can make up for the lower number of protons. So it leads to the same mass number, just like calcium, although it is a completely different element. Both have the same mass number, but different atomic number or different number of protons. Strontium and yttrium, the same thing. So they have a mass number of 90. However, different types, or I'm sorry, different number of protons. So 38 protons for strontium and 39 protons for yttrium. And here 52 neutrons for strontium, 51, but both having a mass number of 90. Quantum properties. Let's talk about the properties of the particles of an atom. First, nuclear spin. What is the nuclear spin? The nuclear spin is the inherent angular momentum. Okay, it is the tendency, or the momentum to rotate, for a particle to rotate around its own axis. Its velocity, angular velocity, during a rotation around its own axis, or spinning motion, if you will, of the atomic nuclei. Now, electrons also have this property, by the way, not only the protons and neutrons. Protons and neutrons within the nucleus have properties like mass, as we started to notice, and the charge, of course, but we add to that another essential property which affects their behavior, and that property is the spin, or the tendency to spin upward and downward around their axis, their respective axis, which is also called angular momentum. Since particles like proton are charged, this spin creates a tiny magnetic field. Why? Because it is the movement of any charge which would create a magnetic field around it. So when a positive charge moves, it kind of changes, or it creates a local magnetic field. A proton has a spin, for instance, of 1/2, saying it spins in one of two possible ways, up or down. A neutron also has a half spin, 1/2 spin. Of course, both are charged differently, or rather, we would say that neutrons are not charged at all. All right, but for a proton, when it moves, it kind of creates a magnetic field participating in the interaction forces between different particles. In pair, if the protons the spins of the protons pair together and cancel out, the nucleus might have no net spin, meaning that they kind of cancel each other, and the nucleus will have, they kind of cancel each other. The nucleus won't have a net nuclear spin. Okay, so the protons spin in pair, or pair spins together and cancel out. Okay, they kind of annihilate each other, so you won't have a net spin, or the net spin would be 0. For instance, a nucleus having the same number of protons and neutrons, the spin will combine, canceling each other, and the nuclear spin of that atom will be 0. That's the most important part here, okay, to take away, because here I might have typed something in a wrong way, or it can be misunderstood. So the point is, a nucleus having the same number of protons and neutrons, the spins will combine, canceling each other. So the net nuclear spin for the nucleus would be, or for the atom, would be 0. Again, so as an example, hydrogen H1 and carbon 13 have a nuclear spin of 1/2, spinning one or of two ways, up or down. But oxygen O16 has a spin of 0. Why? Because the number of protons is the same as the number of neutrons. So the total spins cancel each other. Okay? So if a nucleus has an odd number of protons and or neutrons, it will have a net spin. Why? Because the number between protons and neutrons is different. Otherwise, it will usually have no net spin. Magnetic moment. So what is the magnetic moment? Magnetic moment of a nucleus is born of the spins themselves. As we mentioned, when you have a proton spinning around its own axis, it creates a magnetic field. That's why we talk about magnetic momentum. And orbital rotations, okay, so magnetic moment of a nucleus is born of the spins and orbital rotations of the nucleus, or nucleons, I'm sorry, which make up protons and neutrons around their respective axes. So, the same way the atom has a magnetic moment due to the rotation of negatively charged electrons around its own nucleus, the nucleus itself can have a magnetic moment because of the spins of its protons and neutrons on the inside, each around itself. Protons and neutrons have a magnetic moment themselves due to their spin, contributing to the overall magnetic moment of the entire nucleus. If they cancel each other, the nucleus would have no net spin, as we mentioned. Unlike protons, neutrons have a magnetic moment opposite to their spin, and hence opposite to the spin of protons. So, due to the fact that neutrons are not actually charged particles, they have a magnetic moment opposite to their spin. So the magnetic, if you will, the field vector of the magnetic moment is in the opposite direction of the spin direction, and hence opposite to the spin of protons, for which the angular momentum is in the same direction of their spin. All right, so unlike protons, they have the magnetic moment, the angular moment, all in the same direction. They are charged positively. For neutrons, the magnetic moment is opposite to the spin itself because they are neutral charges. That's one reason. So if you see here, you have protons and neutrons, okay, pairing against each other, and each one, like the proton, has the same magnetic moment direction as the spin itself. Meanwhile, for neutrons, they have an opposite magnetic moment vector turning in the opposite direction. That's why they cancel each other. Here we mentioned that the magnetic moment relationship is mu equal gamma times I. Mu is the magnetic moment. Meanwhile, gamma is called the gyromagnetic ratio, which is constant for each type of nucleus, and I is the nuclear spin, okay, or the total angular momentum of the nucleus deriving from the spins of individual nucleons. So, nuclear magnetic moment is usually expressed in nuclear magnetons, or Muon. What is a nuclear magneton? It is equal to E, which is the elementary charge, times h bar, or the reduced Planck constant, divided by 2 times the mass of a proton. So this is what we define by the nuclear magnetic moment, or a nuclear magneton rather. So the nuclear magneton is equal to elementary charge times constant, the constant of Planck reduced constant, divided by twice the mass of a proton. As a comparison, the magnetic moment of a proton is approximately 1 nuclear magneton, μp equal 1 μn. That of a neutron is equal to minus 0.5 magneton. All right. Let's take carbon-13 for example. This isotope has a nuclear spin I equal 1/2, behaving like a tiny magnet with a moment due to that spin. Now the gyromagnetic ratio is a constant depending on the number of protons and neutrons in the nucleus. For C13, that value is gamma 13C 10.708 megahertz per Tesla. All right, so it is a constant depending on the number of protons and neutrons, as we mentioned. Okay, it's like a frequency ratio, by the way. So we need to convert the gyromagnetic ratio to nuclear magnetons. This is done by, okay, gamma 13C is approximately 0.2675 magneton per Tesla, correct? Now, nuclear magnetic moment is then 0.2675 times 1/2, which is the spin, and hence you get 0.13375 magnetons. correct? So from here we can derive from the gyromagnetic ratio, we can derive the nuclear magnetons, correct? Let's see if we have the relationship. Yeah, from you have the Planck constant, you have elementary charge divided by 2 mp. Okay, actually that relationship cannot give us Muon. Let's take carbon 13 for example. This isotope has a nuclear spin I equal 1 over 2, behaving like a tiny magnet with a moment due to that spin, of course. Now, the gyromagnetic ratio is a constant depending of the number of protons, as we mentioned, in the nucleus. For C13, that value is gamma 13C, approximately 10.708 megahertz per Tesla. Now, we need to convert the gyromagnetic ratio to nuclear magnetons per Tesla. The formula is the following. Mu over mu n, which is the conversion, is equal to 2 pi times gamma, which is this value here. You have 10.708 megahertz per Tesla times 10 to the power 6 times Planck's constant divided by mu n. All right, and you get 0.2675 magnetons, magnetons per Tesla. So the nuclear magnetic moment is then mu 13C is equal gamma 13C, which is the value we got here, times the I, or the number of spins, which gets you 0.13375 Muon, or magnetons. We note here that the true experimental value is actually 0.702, a bit far from 0.13375. But as a review, Muon is equal to the charge, which is elementary charge, times reduced Planck's constant, divided by 2 times the mass of the proton. All right? Quantum properties, half-life. So half-life for a substance is actually the time it takes for half the mass of that substance to decay and transform into another degraded element. This is most common for radioactive decays. Now, for radioactive isotopes, half-life is the time it takes half the amount of atoms to release a particle shifting into a different element or isotope. Now, what we mean by different element or isotope? So as a review, isotopes have the same atomic number Z, or number of protons in other words, and belong to the same element, the same type of substance, but have different mass number. Meanwhile, isobars have the same mass number, A, which is the number of neutrons plus protons, but they are different elements. Why? Because they have a different atomic number. All right, so again, you have the isotope, or isotopes have the same Z atomic number, which is the number of protons. Meanwhile, isobars have the same mass number, which is A, neutron plus protons, and they are different elements. The number of remaining atoms that had not decayed after a time t is given by the relationship n at t after a t time is equal to n0, the original number of atoms, times 1 over 2 to the power of t, which is also the same variable where we are measuring, divided by the time of a half-life, the half-life time constant. So again, t is the number of remaining atoms that had not decayed after a time t. N0 is, or NO is, the original number of atoms. T is the time at which the measurement is taking place. So N is a function of T again. And T 1 over 2 is the half-life time constant for this substance. Of course, it varies from one substance to the other. By monitoring how much radioactivity of a substance had decreased, okay, over time, So we can measure the substance half-life. One of the applications of half-life is carbon dating to identify the age of fossils, as you know, the discovered fossils, to date back a corpse or some type of artifact. We use the same methodology based on measurements of the gradual drop of radioactivity in a sample during a span of time. We can notice an exponential curve when plotting the radioactive levels at constant periods. Why? Because each time you have half of the remaining mass decaying. Then, after the same time span, the remaining half would also decay, and so on and so forth. So based on these observations, we notice that decay is an exponential progression. Each half of the remaining mass, each half-life duration or time span, half of the remaining mass disintegrates or decays rather. Also, half-life itself is a constant time span, meaning that it involves a constant decay rate of half of the remaining mass after each cycle or after each half-life. Let's say half-life is 7 days. So each 7 days, you have half of the remaining mass will decay. Okay, I hope it is clear. So lambda is the decay constant, and half-life T1/2 is the half-life time for a substance. So T1/2 is equal to ln2 divided by lambda, which is the decay constant. All right. So molar mass and atomic mass. Amedeo Avogadro, an Italian scientist who came up with the Avogadro's number, which was named after him, which represents, actually he discovered the number of atoms that are available within 1 mole. 1 mole, okay, it has a different, mass for different atoms, but like it's a specimen size. So within 1 mole, he discovered that the number of atoms is 6.022 times 10 to the power 23 atoms. For each substance, the mass of 1 mole, which is some type of a fixed volume, this is what we call by 1 mole. So for each substance, this mass is different, but having that value along with Avogadro's number, which is a constant, we can calculate by the mass of one atom by dividing the molar mass over the number of atoms packed inside that mole. So you have mass in gram, okay, of one atom is the molar mass, meaning the mass of an entire mole, divided by Avogadro's number, or the number of atoms within that mole. This is how you get the mass for one single atom. Given that the scale in kilograms or even in grams is very unpractical, it would give you very small numbers with huge negative powers, 10 to the power minus 27, as you see here. That's why it is better to refer or to use another scale or reference, which is called the atomic mass unit. So what is the AMU, or atomic mass unit? One atomic mass unit is actually the mass of a proton that we use as a scale, that we use as a reference point. It is the mass of one proton in kilograms. So any other measurements, we divide them by that value to get a more normalized and usable scale called the atomic mass unit. Now here we point to something important, like to give you a clearer idea on why we use AMU, atomic mass unit. The same way, when measuring distances that are very, very large, of a colossal scale, you no longer use meters or centimeters. You would rather tend to use kilometers or miles, or even for astronomical units like astronomical scales, we don't measure distances anymore by meters or kilometers, but we use light years, which is the distance traveled by light during an entire year. So the same concept is used in nuclear physics. Why? Because you have a very low scale that is very small, tiny numbers. That's why we need to measure them in reference of the mass of a proton to get more normalized, more practical numbers. All right, now the mass again of 1 mole can be measured, and when we get the mass of 1 mole, we can actually calculate the mass of one atom of that same substance. How? Again, we divide the molar mass by Avogadro's number, which is a constant, which is the total number of atoms within 1 mole of that substance. So we get the mass for that mole. We get the mass for one atom for that substance, but in terms of kilograms. Now, after that, we need to divide the answer by 1 AMU, or the mass of one proton, which is the reference value that we talked about, which is equal to 1.6605 times 10 to the power minus 27 kilograms, and we get the value in AMU, or atomic mass unit. So taking an example, you have the sodium Na. The mass of 1 mole of a sodium is equal to 22.99 grams per mole. Okay, now we take that, we divide it by Avogadro's number, 22.99 times 10 to the power minus 3. Why? Because we need to convert it to kilograms. It is in grams. We divide by Avogadro's number, and you get 3.81766 times 10 to the power minus 26 kilograms. Now, to get that value in atomic mass unit, you divide the answer by the mass of one proton, or the AMU again, which is 1.6605 times 10 to the power of minus 27 kilograms, and this is the answer, 22.99 AMU. And by the way, here as a note, the mass of sodium chloride would be the masses of the sum of masses of the sodium plus the mass of chloride. All right? Einstein's equation E equal mc squared. Stemming from Einstein's theory of relativity, a small amount of mass can be converted to an enormous amount of energy at the speed of light, and vice versa. In other words, mass and energy are interchangeable. So suppose you have 2 kilograms of substance, how much energy will it form at the speed of light? So E equal mc squared, you have 2 times 10 to the power 3, because it's in kilograms, times 3 times 10 to the power of 8 meter per second square, which is the speed of light, but in terms of meters per second. Then E, or energy, is equal 18 times 10 to the power 19 joules. Okay. Now, in nuclear physics, it's more practical actually to work with another scale for more practical measurements. Now, the unit for that is the mega electron volt, or MeV. Instead of multiplying the mass with the speed of light in meter per second, we know, or we have found out, that for each AMU, for each 1 AMU, or atomic mass unit, the conversion of that 1 U to energy would give us 931.5 mega electron volts. So each 1 AMU converts to 931.5 mega electron volts. That's how, by having that value, you need to calculate to measure the mass that's being converted to AMU, or atomic mass unit, and then you multiply it by 931.5 mega electron volts. So we replace the speed of light, which is expressed here in meter per second, by 931.5 mega electron volts, given that the mass is no longer calculated in kilograms but in AMU. So in nuclear reactions such as fission, fusion, and decay, only a partial mass of the reactants is converted to energy. This partial mass is defined by the term mass deficit, delta M, which is the value of mass difference between reactants and the products. Okay, so the reactants are the substance, the sum of substance that are on the left of the equation. The products are what is being produced to the right of the equation, or like the chemical reaction. So therefore, Einstein's equation becomes the following: E equal delta m c square, with delta m is the mass deficit, okay, multiplied by, again, instead of c square, you replace it with 931.5 mega electron volts. And again, delta m is called technically the mass deficit, which is the difference between the mass of the reactants and the mass of all of the reactants and the sum of mass of all the products of the reaction. And again, we multiplied by 931.5 mega electron volt to get the energy value in mega electron volts. All right, let's talk about different nuclear processes, nuclear reactions. Starting here by nuclear decay. So what is a nuclear decay? Nuclear decay is a process that occurs for an unstable atom where a particle breaks from the atom, releasing energy and transforming the nucleus into a more stable one. Why? Because it had released the overweight, if you will, or into a different atom. So into a different isotope of the same element, or a different atom designated or defined by isobar. So the nucleus of the element undergoing the decay process is designated as radioactive or unstable. Both terms we can use. In the next page, we start listing different types of nuclear decays and the emissions they involve, based on the number of particles being released and the main particles that is in play. Starting with alpha decay. Alpha particle is actually the release of 2 protons and 2 neutrons. Okay, so this type of decay involves the release of 2 protons and 2 neutrons identical to a helium nucleus, He4. Why? Because when we talk about 2 protons, that is the atomic number, Z equal 2, and 2 neutrons, you add them to the 2 protons, so you have in the atom, the mass number, you have 4. So this is identical to helium He42 particle. All right? So again, you have the release of 2 protons and 2 neutrons, identical to helium nucleus. The atomic number decreases by 2. Here, meaning from the reactant, it decreased by 2, and mass number by 4 in the example below. So you have 2 protons and 2 neutrons breaking off an unstable uranium nucleus, which transforms into thorium while releasing an alpha particle. Here we note something, that the number of protons and neutrons need to be conserved, meaning that if you add up all the protons between the reactants and the products, you have 92 here, you have 90 plus 2. So it's the same number, however, they are broken into 2 lighter elements instead of 1. And the same thing here, because we have the release of 2 neutrons as well. Those 2 neutrons are taken also from the mass number for the thorium, which has lost on one hand 2 protons and on another 2 neutrons. So it has been lost from the mass number. That's why it is 238 minus 4, which is 234. And these lost protons and neutrons have converted into a moderately heavy particle, which is the alpha particle or helium. Now let's calculate the energy burst out of this reaction. So we need to evaluate the mass deficit, which is E equal delta m c square, delta m being the mass deficit or the difference of masses between the reactants and that of the products. So mass of uranium, which is U238 here, is 3.952 times 10 to the power minus 25 kilograms. We'll get them in kilograms at first. Mass of thorium 234 is 3.889 times 10 to the power minus 25 kilograms. And mass of helium 4 is 6.646 times 10 to the power minus 27 kilograms. So we need to simply divide them, actually, yeah, because here is the mass of one atom. So we divide them by the atomic mass unit to get their value in AMU. So starting with the mass of uranium, you have 3.952 times 10 to the power minus 25. That's the mass of one atom of U-238. You divide it by the scale, which is the AMU, 1 AMU is 1.6605 times 10 to the power minus 27 kilograms. You get 238.05 AMU. A relatively heavy atom, as you notice here. Okay, for helium, the same way, we divide the mass of helium in kilograms by the mass of AMU. You get 4.0026 AMU. Mass of thorium, the same thing. You divide here the value in kilograms, which is 3.889 times 10 to the power minus 25, divided by 1 AMU, which is 1.6605 times 10 to the power minus 27, giving you 234 times 0.0436 AMU. So here we can now evaluate the difference of masses between the reactants and the products. So let's do that. So mass of uranium, thorium, helium. Okay, delta M is equal to the mass of reactants minus mass of the products, which is mass of U-238 minus the mass of 234, okay, plus the mass of thorium, 234 plus the mass of helium. So 238 minus 234.0436, you see it is close to the mass number, plus 4.0026, which is the mass of of a helium atom. All right, so the mass deficit is equal to 0.0038. So the energy is equal to delta MC square equal to 0.0038 AMU times what? Multiplied by the 931.5 mega electron volts, giving us 3.5397 mega electron volts. You have an element having an atomic number Z and a mass number A decaying into a lower weight element while losing 2 protons from the atomic number, so Z minus 2, and 2 neutrons. Add them to 2 protons, you have 4 missing from the mass number. All right, so you get a completely different element while releasing an alpha particle, which is a helium-4 corresponding to a helium-4 particle, having 2 protons and 2 neutrons, which you add them to the protons, you get 4 in the mass number. And of course, the atomic number is Z equal 2. Beta decay or beta minus decay in such case, a neutron within the element in this nuclear process transforms into a proton, adding up the positive charges of the generated atom. That's why you have in the product the atomic number is added by 1. But as a result, it also, to achieve equilibrium, it emits a beta particle, which is an electron or negatron plus an antineutrino, which is designated by this symbol, nu bar E. All right, so to give you an example for that, when you have a C14-6, the carbon element, it decays into a nitrogen element having an atomic number of 7, mass number 14. You see the mass number is still the same. It did not change. Plus E minus plus 1 antineutrino. So if you add up, if you notice something at first, you have, since the atomic number is the designator of the type of matter, it's like the unique identifier of the matter. Because this atomic number Z has changed, it was added by 1, it shifts the type of atom into a completely different substance, which is nitrogen. Okay, it was carbon, it shifted into nitrogen, plus the release of one electron, one antineutrino. The mass of carbon C14 is at first 14.0032419888 AMU. Mass of N14, okay, the nitrogen, almost the same mass, 14.00307. Mass of electron is this value. Here we're trying to get the energy from that type of decay, which is a very low energy, but nevertheless. So delta M is equal to mass of reactants minus the mass of products, M14C, minus M14N, plus the mass of the electron, given that, because, you know, the mass of antineutrino is 0. It doesn't have any mass. It's so negligible. Okay, so delta M is equal, which is the mass deficit, is equal to 0.00038059. So E equal delta M C square, or delta M times 931.5 mega electron volts, which is 0.354525, you know, mega electron volts. Okay, great. Another beta decay reaction is that of cobalt, CO60, where it transforms into nickel. You see how that type of decay changes the type of matter, changes the matter into a completely different element. All right, so here in this reaction you have cobalt, which is, you know, right below iron. All right, some levels below iron. So it transforms into nickel through, you know, the beta decay, which is also unstable and radioactive. But let's start with the first reaction, CO6027. It shifts into nickel 6028, and that proton that is added into the atomic number is negated by the release of one electron plus one antineutrino. Here the same thing, we're trying to measure the mass deficit and also as a result the energy that comes from that reaction. So mass deficit here, you know, you can look up the mass in atomic mass unit for different elements on Google. Okay, we're not gonna calculate for each one every time, convert from kilograms to AMU. It's better to get them in AMU. All right, so delta M is equal to mass of reactants minus mass of the products, which is the mass of cobalt 60 minus mass of nickel plus mass of the electron together, taken from the mass of the cobalt, around 0.002487, which is the mass deficit. By the way, I get many numbers after the comma. Why? Because we're talking about very tiny numbers. So you cannot round it up, otherwise you end up with wrong values. All right, because these values here matter. So E equal delta M times 931.5 mega electron volts, which is 2.3168 mega electron volts. All right. Gamma decay. Now, for gamma decay, that's when an atom releases a gamma ray, which is a high energy photon, but this does not affect its atomic mass number or its atomic number or the mass number, atomic number Z or mass number A. As we noticed in the previous example, cobalt decays into nickel, which then becomes in an excited state. So nickel then decays again, releasing a gamma radiation, which is a high energy photon, but it doesn't touch the mass number or the atomic number. We still end up with almost, you know, the same type of atom. So you have, for instance, gamma decay. What's gamma decay? Is an atom release or gamma ray, which is a high energy photon. It does not result in any change of its atomic, you know, of the atomic number or mass number of the atom. As we noticed in the previous example, again, cobalt had decayed into nickel, which is still radioactive. So what happens then is that the nickel decays again without any change in the mass number or the atomic number, but it becomes less radioactive while releasing a gamma energy, a gamma radiation, which is a high energy photon, okay? Because it was excited, you know, it was the electrons actually were at a high level, high atomic not yeah high energy level rather, okay. They release, okay, when they fall back to the meta state, they release a photon, okay, but without any change again in Z or A. Neutron emission. Now this occurs in a nuclei with an excessive number of neutrons within the nucleus or during certain nuclear reactions. Okay, in the following example, we observe the neutron emission from an unstable californium, actually in the next page. Okay, but let's first observe the reaction, okay, the equation of the reaction. So we have XAZ, it decays into another, you know, actually another isotope while losing one neutron, plus that neutron is actually, you know, released. So it breaks off from the atom and it's released freely. It only changes the mass number, rendering the new product into a new isotope of the same type of element. So for instance, you have this reaction, californium CF25298. It decays into, you know, a lighter version, a lighter isotope, CF25198, while releasing one neutron. So also we can measure the mass deficit, and after that the energy value. You can do that if you will. So mass of CF252, 252.08, here 251.079, which is CF251, and that's the mass of the neutron. So again, we take the mass of 251 CF plus Mn, we take it from the mass of californium 252, we multiply that, meaning that we do the subtraction, we multiply the value by 931.5. The point is the energy is 6.1729 mega electron volts. Another type of decay is photon emission, which is not, yeah, but actually, yes, it is a beta plus decay. So it's a rare process that occurs in proton-rich nuclei. So when you have a nuclei rich with protons, it can decay while releasing, you know, one proton, and as a result, the atomic number Z decreases by one, giving birth to another element. So let's say you have C611. Okay, actually, yeah, one proton breaks off from Z, which is the atomic number, correct? So this proton is released as beta plus particle. Also, another name for it, positron plus neutrino instead of antineutrino, giving birth actually, or converting the carbon into Bohr element, okay, having a different atomic number, of course. When you have a different Z, you have a different element. And we measured the energy here is 1.4714 mega electron volts. Okay, electron capture, that's a process when a proton in the nucleus captures an inner orbital electron, transforming it into a neutron. All right, so while emitting a neutrino. So you have here, okay, XAZ plus one electron, you have a you know, Z minus one, okay, within the atomic number plus neutrino. Example for that, the beryllium 7, which when it captures an electron transformed to lithium 7,3. So you have one proton has been lost, okay, plus a neutrino here, okay. And also no need to do the same calculations all over again. Okay, here we note something again, that the neutrino, okay, transform it, okay, so the orbital electron, the nucleus, yeah, captures an inner orbital electron, transforms it into a neutron. This decreases the charge by 1. This is what's happening. All right? Spontaneous fission, it is when an unstable, very heavy nucleus splits into two or more lighter nuclei while releasing neutrons and a very high energy. All right? But not necessarily, here we're not talking about nuclear fission that is triggered by the bombardment of a neutron. Actually, here we're talking about, perhaps it happens within the process of nuclear fission, but it's when you have a uranium, for instance, 23892, very unstable. Okay, it decays into lower atoms, lower types of matter, such as the xenon, strontium, while releasing 4 neutrons and very high energy. Actually, these neutrons will actually also participate in triggering or bombarding other atoms to cause a chain reaction, which actually leads to a huge explosion of the nuclear bomb. So, at first, let's calculate the mass deficit. Mass of U238, xenon 140, we have all these values. So M238 minus the mass of all the products, which is 140 xenon plus M94 strontium plus 4 Mn, 4 times mass of the neutrons, because you have 4 neutrons, which gives you 0.179 AMU, okay? Multiplied by 931.5 mega electron volts, you get 166.858 mega electron volts, which is a very significant energy. All right, it's a very significant energy for one atom of uranium. Okay, and you multiply that by a much larger number of mass, you get something, you know, very, like, you get an energy that can destroy an entire city. Actually, this is how nuclear fission works. All right, so another, yeah. Here we're talking about a triggered nuclear fission. So nuclear fission that is triggered, it happens when a heavy radioactive nucleus is bombarded, meaning that you shoot it by a neutron, which is, by the way, since it is heavy and radioactive, it's unstable. So the minimum impact of another particle against that nucleus, given that it's unstable, it's radioactive, it's heavy, all right? Unstable meaning that it's at the verge of breaking off, okay? It's not in, you know, a natural equilibrium. So the neutron will split it into, will split whatever that atom, in such case, in our case, it is the uranium-235. So it would split it into 2 smaller atoms with neutrons and, you know, the release of neutrons and a very high energy. This is the same reaction triggered to detonate a nuclear bomb. So let's check here the energy that is generated. So again, you add the mass of uranium to the mass of 1 neutron here, minus the mass of barium, krypton, yes, and plus 3 times the mass of neutrons, because you have 3 neutrons released, and you get 173.289 mega electron volts. Now, these 3 neutrons released will also go and come against other nucleus, other, like uranium nucleus, all right, uranium atoms, triggering again a chain reaction, causing, you know, one fission after the other, generating a massive amount of energy. Now, nuclear fusion. Nuclear fusion is the main reaction taking place within stars like our sun in the solar system. It is actually the process when 2 light atomic nuclei fuse together or combine, forming a much heavier atom, but the reaction or the result of that process is the release of a much vaster, a much heavy, you know, colossal amount of energy, even way bigger than the energy released by the fission process. You know, that's counterintuitive, but actually, yes, this is what happens. In fusion, you have a release of a much higher energy, way more than in fission. So here, it's one of the reactions happening inside the sun. You have one deuterium, okay, fusing with tritium, I think, okay. It leads or it forms helium-4, which is an alpha particle, plus one neutron, plus 17.6 mega electron volts. Now, you would think that 17.6 is a very small value. Actually, we're talking about only, like, these are very light particles or atoms we're talking about. Like, it's unlikely for a deuterium and a tritium to release 17.6 mega electrovolt amount of energy, especially that we're talking about very light atoms. All right. Now let's talk about subatomic particles. So at first, subatomic particles are particles smaller than atoms that make up all matter. And they involve different force interactions in the cosmos. They include protons, neutrons, electrons, but also other smaller and lighter particles. We've seen some of that previously, but we're talking about like the particles that make up the neutron and the protons themselves. This was discovered by smashing these types of particles, such as the protons, okay, against each other in the LHC, the Large Hadronic Collider in CERN. By smashing these two particles, we notice that there are even smaller particles making up these two, okay? This is what's interesting about subatomic physics. All right, but at first let's talk about quantum states for subatomic particles. And what do we mean by them? A quantum state describes different properties of a system. These include position, momentum, all right, energy, and spin. And they are represented by a wave function C. All right, the states can be a pure state described by a single wave function that is stable, or a mixed state of several pure states. Okay, it's a combination of different pure states. So you have, again, as we mentioned, the quantum state describes properties of a system or a particle, like the position, again, momentum, the energy, and spin that we've previously talked about. So quantum number, let's talk about these different values. So you have the principal, symbolized by n, which represents the energy level or shell number. Also, like the energy level for electrons here, we're talking, okay? The electron is represented by an energy level, meaning that what orbit is it using to revolve around the nucleus. So the closest orbit, which is the lowest altitude closest to the nucleus, is level 1. You have second level, or the second orbit, which is a bit further, is level 2. 3, okay, the third is level 3, 4, etc. Okay, this is what we're talking about. Actually, the electron is released once it reaches the highest energy level. It's released from the atom and it's a free electron. Now, angular momentum, or L, it is the shape of orbital. What is the shape of the orbit? Okay, we have different designations here. The allowed values is L is between 0, so 0 angular momentum, or a value which is n, okay? So it is windows between 0 and n, all right? Magnetic, which is the magnetic force, okay, orbital orientation in space, okay, or if you will, the orientation of the vector in the space. So here ml is between minus L, negative orientation, or positive L. And finally, the spin, symbolized by m lowercase s, intrinsic spin of the particle around its own axis, as we mentioned. So you have plus 1 over 2 or minus 1 over 2. Okay, types of quantum states. So you have stationary state, which is, energy eigenstates, unchanging probability distribution in time, meaning that it is a stable state, is stationary, it doesn't change in time. It has the same probabilistic distribution like an electron in a fixed orbital around the nucleus. Okay, so it is fixed. It's not fixed actually, it's rotating, but it has the same probabilistic distribution throughout time. All right, now second state is the superposition state. In such case, a particle can exist in a combination of multiple quantum states. The state is a combined multiple quantum states. C, which is the representation again of the wave function, is equal to A1 times C1, it's one wave function, plus A2, another factor, multiplied by another wave function. So both of them combined, they represent C, not only one. Entangled states, this is the quantum state of two or more particles, such as the state of one affects the other. So here what we have is an entangled state. You have, let's say, two or more particles. The state of each particle cannot be described without the states of the other particles, because each particle state affects the states of all the other particles. Why? Because they are connected, they are interdependent state-wise. All right, so the state of one affects the other and they are dependent upon each other. That's why we call it entangled state, because they are entangled together. The change of the state of one particle affect all the other particles. Coherent state, which has minimal uncertainty. Incoherent state, statistical random mixtures with different phase relations. Mixed state represent a density matrix, not a single wave function. This is when, the system is part of another much complex entanglement. Okay, that is not known, but we see that you have a matrix distribution of the states. Okay, it's not one state or another. You have a matrix. Okay, the relationship here is very complex. So again, coherent state, you have like a much stable state, minimal uncertainty values for the probabilistic distributions. For incoherent states, you have statistical random mixtures with different phase relations. Subatomic particles, fermions. Fermions, which are matter particles, they have half-integer spin, e.g. 1 over 2. They include quarks and leptons. Fermions are the fundamental building blocks of matter. They obey Pauli exclusion principle, which states that two identical fermions cannot occupy the same quantum state at the same time. An example for that is electrons that orbit an atomic nucleus. They cannot occupy the same orbital. Fermions are made of quarks and leptons. All right, so let's start with quarks, because fermions are made of quarks and leptons. So in quarks, you have 6 types, or 6 flavors as we call them. So you have different names for them, and the names do not designate any type of behavior or mass, but they rather come from an ancient naming system in astronomy. Okay, ancient conventions, if you will. At first, you have up, symbol U, and the charge is positive. You can say that up, it was called like that because it has an upper charge, a positive charge greater than 0, which is plus 2/3, the mass around 2.2 mega electron volts c square. All the spins for all the quarks are 1/2. Down, the down particle has a negative charge. That's why perhaps it is down. It's called down. So minus 1/3 the charge. The mass is around 4.7 mega electron volts per c square. As you notice, up and down particles are very light. Now charm, denoted by C, has a charge of plus 2/3 and a very large mass. That's why perhaps it is charm. The mass is around 1270 mega electron volt per c square. Strange, denoted by S, has a negative charge, -1/3, around 96 mega electron volts. The mass per c square. Top, or T, has a positive charge of +2/3, a very huge mass of 173,000 mega electron volts per c square. Perhaps that's why they call it top. By the way, it occurs for a very short time and then it decays instantly, this particle. Okay, so it is very heavy, but it occurs for a very short period and then disappears. Bottom, B, a charge which is negative -1/3. The mass is around 4180 mega electron volts per c square. Now, up and down form baryons, which are like the protons and neutrons. What do we mean by that? The proton and neutron are made of even smaller particles, which are the baryons, which are the up and down flavors. So a proton is made of up, and down. If you add up the charges, okay, up, and down, meaning +2/3, +2/3, -1/3, it gives you +1, which is a positive charge. As for the neutron, it's made of up, down, so +2/3, -1/3, -1/3. You sum it up and you get a neutral charge, which is the charge of neutron. So up and down are light and they make up stable matter, like protons and neutrons. Top is extremely heavy, but it is unstable, existing for a very short period of time after a high energy reaction. Quarks combine to form hadrons, such as baryons, so proton and neutron. We call them hadrons, and particularly baryons. Okay, proton up, down, neutron up, down, and mesons also are formed from quarks, which are quark-antiquark pairs. The other type of fermions is leptons, also 6 flavors. Now, unlike quarks, leptons are not affected by the strong nuclear force, which is a force that binds protons and neutrons together. It's like an extreme, like a powerful force that pulls them together. Not a magnetic force or a gravity, that's something else, but it's called a nuclear force because it is at the nuclear level. So they are not affected by that force, and most of leptons are very light common particles like electrons and neutrinos, but they are not like drawn or pulled by the strong nuclear force, unlike the protons and neutrons, for example, in the nucleus. So here we mention 5 of these particles or flavors. You have the electron, obviously. So symbol E minus, of course, the charge is -1. And here the charges are an integer value. So the mass is 0.511 mega electron volt per c square. The spin is 1/2. Electron neutrino, which is nu e without a charge, meaning it is a neutral charge. It is very, very light, which is around 0.5022 mega electron volt per c square. Spin 1/2. Muon neutrino, which is nu mu, the charge nu mu, the charge is also 0, less than 0.17 mega electron volts. Tau, which is tau minus, okay, the charge is negative here, so only for electrons. And tau, the charge is negative, but here, interestingly enough, the tau has a very huge mass. It is very heavy, 1776.86 mega electron volts per c square. And finally, tau neutrino, which is nu tau, charge 0, less than 18.2 mega electron volts. As a comparison between quarks and leptons, so here they differ, these two types of particles, by multiple levels. One of them being the role, then the charge, the experiencing or the interaction with the strong nuclear force. Can they exist freely or not? Number of flavors, actually it's not a difference for the number of flavors, both have 6. And the interactions, and finally the composite. Okay, so let's start with the fundamental role. For quarks, they combine to form protons neutrons, and mesons. As for leptons, they can be found alone, meaning like electrons and neutrinos can be roaming freely. Now, the electric charge, here the quarks have a fractional charge, meaning that they would be plus 2/3 minus 2/3 plus 1/3 minus 1/3, so it's a fractional. Meanwhile, the leptons have an integer charge, either 0 or +1 or -1. For quarks, they experience strong nuclear force, so yes, they carry what we call a colored charge, but for leptons, they are not like affected by that strong nuclear force. Actually, they have their own weak electromagnetic, they interact with a weak electromagnetic force and also gravity. Weak force, weak nuclear force, electromagnetic, which is charge, or gravity. Okay, so can exist freely if they are charged. Okay, can they exist freely? No, because quarks are confined in hadrons. They make up hadrons. They are parts of a bigger thing, like just like up, down, down, form the proton. Okay, so they cannot fly freely in space. They make up bigger particles like hadrons. As for leptons, yes, electrons and neutrinos are free. An example for that is the neutron star. Actually, no, the neutron star is a neutron formed of lower level particles, but so to speak, negative charges such as electrons and like neutral charges like neutrinos can be roaming freely in space without any binding. Number of flavors for both, 6. For quarks, you have up, down, charm, strange, top, bottom. As for leptons, you have electron, muon, tau, and their neutrinos. Interactions. Now, for the quarks, they interact with all 4 forces. Among them, the strong nuclear force, the weak nuclear force, electromagnetic force, and gravity. As for leptons, they interact with weak nuclear force, electromagnetic, for the charged particles, and gravity, but the strong nuclear force has no effect on them, and we'll explain in the next slide the difference between strong and weak nuclear forces. Composite, no, but they form composite particles such as neutrons and protons. As for leptons, also no composite, they are elementary and not bound in hadrons. Strong versus weak nuclear forces. So, strong and weak nuclear forces are fundamental in nature. Other forces, of course, are the electromagnetic force and the gravity. These two types differ by reason of strength, range, role, and the particles they can influence. Now, starting from strength. For the strong nuclear force, they are the strongest of all forces. Why? Because they bind particles like neutrons and protons together with a huge pull, with a huge force. However, they have a short range. We're gonna see that. As for weak nuclear force, they are much weaker, 10 to the power minus 6 times than the strength of the strong nuclear force. For the range is very short for strong nuclear force, around 1 femtometer or 10 to the power minus 15 meters. So it is a force that has its power or effect at a very nuclear level, at a very particle level. Again, it is the force that holds a nucleus together. All right, but its range is very small. As for the weak nuclear force, it is even extremely short, around 0.001 femtometer. The force carrier, which is the particle, so to speak, that carries such force, is the gluons. The gluons are the particles that hold the nucleus together. For the weak nuclear force, this force is carried by particles such as W+, W-, and Z0 bosons. Bosons are actually particles that carry force interactions. Now, the strong nuclear force acts on quarks and particles with scalar charge, but the weak nuclear force acts on all fermions, especially quarks and neutrinos, because the weak nuclear force interacts with all type of fermions, especially quarks and neutrinos. So all particles that are among the fermions, as we mentioned. The main role: the strong nuclear force binds quarks into protons and neutrons. So it binds the quarks, which are up, down, I think, for protons, and up, down, down for neutrons. They bind these particles together, okay, to form a proton and a neutron. That is the main role of the strong nuclear force. But more than that, it holds the nucleus together, the nucleus of the atom. So you see how important the strong nuclear force is. It is the very force that binds these quarks together to form protons and neutrons. And again, as a reminder, like what forms the protons is actually 2 ups and 1 down among these fermions, which are the quarks. As for the weak nuclear force, it causes beta decay and neutrino interactions. Now, the strong nuclear force is involved in nuclear binding and the formation of hadron, formation of protons and neutrons, correct? So, meanwhile, for the weak nuclear force, it is its main role is triggering the radioactive decay, okay? Because it's weak, but still it has an effect to break a particle off, to cause a radioactive decay, especially interacting on beta decays, okay? Like plucking out an electron from the nucleus and all, other types of decays. Bosons. Okay, this type of particles are actually, the bosons are actually force carriers. They carry force. Bosons have an integer spin, meaning 1 or 0, or 2 for the graviton, which is a little bit theoretical. They are the force carriers in nature. They are the particles that actually carry force. So let's examine them. The photon is actually a boson. The force carried is the electromagnetic force, as we've seen and as we know. You've heard of the electromagnetic power generated by the sun, the electromagnetic storm. This is caused and triggered by the photon particle, which is, a high energy radiation. Okay, the charge is 0. It has no charge. The mass is also 0. The spin is 1. Gluon, G, the force carried is the strong nuclear force, because it is the gluon that holds a nucleus together, and it is the gluon that holds the different lower level particles, subatomic particles such as the quarks, together to form protons and neutrons. The charge is 0, mass 0, and spin is 1. W boson, W plus minus, the force carried is the weak nuclear force, which triggers again the radioactive decay. Charge plus or minus 1, both, and the mass is around 80.4 mega electron volts. The spin is 1. Okay, it's a little bit heavy. The Z boson, Z0, also force carried is weak nuclear force. The charge is 0, the mass around 91.2 mega electron volts, spin is 1. Higgs boson, H. Okay, the force carried is generation of mass. It generates mass within the matter. All right, the charge is 0 and the mass around 125 mega electron volts, so very heavy, which makes sense because the Higgs boson is actually has the force of mass generation within matter. The spin is 0. Graviton, which is, the particle connected with the power of gravity. The charge is 0. Mass assumed to be 0. The spin is 2. It is more theoretical still. All right, so we've already seen or listed the most common reactions such as nuclear decay, fission, and fusion. The following is a sequel for that occurring on the particle level rather than the atomic level. All right, so let's see these subatomic reactions. Annihilation, which is one positron and one negatron, particle or anti-particle smashed together, annihilate each other, producing 2 gamma radiation particles. So it's a high energy transformation actually. And it can be triggered actually through the particle accelerator. Quark level beta decay, you have down produces up, then W minus, then transforms into an electron and an antineutrino. Neutrino scattering, so you have the new mu, okay, neutrino, muon neutrino plus one neutron, it gives muon plus proton. Also a muon decays into an electron, releasing an electron, an antineutrino plus a muon neutrino. So let's start with the annihilation. So one positron and one negatron collide together, particle and antiparticle, annihilating each other, producing two gamma radiation particles. The mass of electron or positron and negatron, if you will, E plus and E minus, is the same, which is 5.485799 times 10 to the power minus 4. The mass of gamma is 0, so delta M, let's see, check the energy, is mass of the reactants minus 0, because the mass of the products is 0. It's almost a pure energy here. So it gives you 10.9715 times 10 to the power minus 4 AMU, and E equal delta M times 931.5 mega electron volts, which is 1.022 mega electron volts. That's the power generated from that. Neutrino scattering, okay, mu plus one neutron, it produces one muon plus a proton. Okay, here the different masses of these particles. So delta M equal the mass of reactants, which is mu nu plus the neutron here, minus mass of the muon plus mass of the proton. Okay, so we run the math, we run the number, you get 0.1120 and AMU. Okay, so E equal delta M times 931.5 mega electron volts, which is 104.365 mega electron volt. Actually, it's a very powerful reaction, and it produces high energy for very, tiny particles and very like low heaviness, low weight particles, such as the mu, the neutrino mu. All right, so it produces relatively a heavy or an energetic reaction. Okay, a massive energy. Muon decay, okay, so the muon decays into a negatron plus antineutrino plus nu mu, which is the muon neutrino. All right, so also we list the different masses in atomic mass unit for different particles, and you are free to run the numbers yourself to calculate. So delta M is equal to the mass of the muon minus the total mass of the products, which is mass of the electron plus mass of the antineutrino plus mass of nu mu, okay, which is equal 0.8943. okay, AMU E equal delta M times 931.5, 833.129 mega electron volts. That's a very powerful reaction. That's a very, it's a very high energy being produced here, like, interestingly enough. All right, so how much energy would that make in terms of TNT explosion? The number we got from the previous page, from this reaction. So 1 grams of TNT, because it's interesting to calculate the energy you get in terms of TNT grams, okay, or TNT explosion. So 1 grams of TNT releases approximately 4,184 joules. So 1 joule is equivalent to 1 by 4184, meaning that 1 gram divided by this amount of joules, which gives you 2.39 times 10 to the power minus 4 grams of TNT per joule, okay, per joule. So this amount produces 1 joule. So 1 electron volt is equal to 1.602 times 10 to the power minus 19 joules. So we are about to convert from mega electron volt to joules to TNT grams. So let's convert 833.12998841 mega electron volts to joules. So you multiply them by, first of all, 10 to the power 6 because it's a mega electron volt. Then, as we know, 1 electron volt is equivalent to 1.602 times 10 to the power minus 19 joules. So you multiply that value by that number. You get 1.33467 times 10 to the power minus 16 joules. So as a result, okay, and by comparison here to the grams of TNT, yeah, you divide that value by 2.39 times 10 to the power minus 4, all right? So what you get is around, actually, yeah, one moment, so minus 16 joules. Okay, so you divide it by, yeah, 2.39, okay, this is 1 joule. Yeah, you actually multiply it by 2.39 times 10 to the power minus 4 grams of TNT. Why? Because each 1 joule produces 2.39 times 10 to the power minus 4 grams of TNT power. So you get 3.2 times 10 to the power minus 20 TNT grams, equivalent explosion. All right, in particle interactions, charge, baryon number, lepton number, and energy and momentum are conserved. All right, so the baryon number, the lepton number, energy, and momentum are conserved. What changes often is the quark flavor, the type of quark, meaning if up, it might flip to down, or parity. So, first of all, let's check what would be the binding energy of a nuclei. The binding energy of a nuclei, E binding, is equal to Z, or atomic mass number, times the mass of the proton, plus N, which is actually the number of neutrons, times the mass of a neutron, minus the mass of the nucleus itself, which is, again, an atomic mass unit, depending on the type of matter, times C square. And this is how you get the binding energy of the atom. So again, it's equal to Z, atomic mass number, times mass of the proton, plus N, which is the number of neutrons times mass of the neutron, minus mass of the nucleus, all right, depending on the type of matter, times C square. Probability of flavor change of distance. Okay, flavor change means a muon neutrino can change into electron or tau neutrino. So what is the probability of the flipping between flavors, all right, at a distance L? That's an interesting one. So the probability is equal to a probability of switching of flavor, okay, from neutrino alpha to neutrino beta, for example, is equal to sinus or sine square 2 theta, theta is the mixing angle, times sine square 1.27 multiplied by delta m square, which is the mass square deficit, times L, which is the distance in kilometers, divided by the energy in giga electron volts. So the probability of the transition of one flavor to another, okay, from neutrino something to antineutrino to something else, is equal to sine square of 2 theta, theta being the mixing angle, times sine square 1.27 multiplied by the mass deficit square, times L, which is the distance in kilometer, divided by the energy in giga electrovolt. All right, cross section sigma. The cross section is actually the measurement of probability that an interaction or collision will occur between a particle, an incident particle, and a static particle within, a specific area. So it's a dependent factor on the number of interactions per second, or interaction density, or incident flux, which is the number of particles incident particles going per second per unit area, all right? And finally, which is phi by the way, and finally the number of target particles that are, the targets that are located in also a unit area. So let's back up a little bit. Sigma, or the cross section, is equal to, or is dependent upon, R, which is the number of interactions or interaction density per second, the number of possible interactions per second. Then also the incident flux, or number of particles traversing a unit area, let's say 5 centimeters square, for example, per second, okay? And number of target particles, like the number of particles that are the target that are located in that 5 centimeters square, all right? This is the analogy for that. So sigma is equal to R, which is again the number of interactions per second, divided by phi, or flux of incident particles. Again, it's the number of particles crossing an area, let's say 1 centimeter square per second, times n, which is the number of targets located in that area. Great. So it gives you something like a probability factor of collision or interactions per unit area. Now, let's state some of the nuclear reactions in the sun. So in the sun, you have the fusion. The main reaction is the fusion reaction. It starts with a proton fusing with one proton, and this goes in sequence in a chain reaction all the way to producing heavy metals such as iron and nickel, which are, the final state of the fusion. All the way, and also you have other types of reactions such as photon, such as decay, electron capture, dissipation, that forms all types of matters that you see. Now, it starts again from the proton-proton fusion. One proton fuses with another proton, producing helium-2 plus positron plus a neutrino. This is the first reaction producing the first helium here. Then, or deuterium, we call it, He2, proton-deuterium fusion. Also, the deuterium that was formed will fuse with another proton, forming helium-3 plus gamma. The gamma here is actually the photon that produces light. This is the reaction that starts producing light within the sun. After that, helium-3, also another reaction going on. Helium-3 fuses with another helium-3 and produces helium-4, okay, with 2 released protons, 2H1, meaning that also participate in recreating the cycle of reactions. Now, for helium-4, it fuses from this point on, by the way, all right, the fusion will no longer produce much light or recreate protons, okay, to recreate the cycle. It's still producing some light, however, but the cycle is no longer being, recreated, meaning that it's no longer adding to the fuel to reproduce light. So helium-4 fusion produces barium, which is a heavy atom, plus a gamma radiation. But as you start seeing, you get to a point where you're no longer even producing light, okay, but only heavier and heavier substance. So helium-4 burning produces carbon. C12 fusing with helium-4 produces oxygen. You see, helium-4 burning produces carbon. Carbon fusing with helium-4 produces oxygen. Oxygen with helium-4 produces neon. And you get from heavy to even heavier substance. Carbon burning produces in another reaction when it fuses among itself. It produces sodium plus proton, and you have the oxygen burning. It fusing with itself produces silicon plus helium-4. Finally, the silicon burning produces nickel, which is a heavy metal plus 2 protons, and the nickel also it transforms, because it has a very short life, it decays actually into cobalt, then the cobalt into iron, Fe56, while also producing a gamma radiation. Now the nickel, I think it has yeah, around 7-day half-life. Okay, after that it decays into cobalt, and for cobalt it has, I think, 70 days half-life, around that. After that it decays into iron, and both of the reactions are also producing gamma. But this is how you get the heavy metals within every element, within nature. Okay, they all come from the decay of the star, because after that actually, and this one is after a supernova, these two reactions. So the star explodes, shedding everything to the outside. Most of these metals that have formed, they are expelled, okay, and they become abundant around the star. Some of them, the heavy metals will start forming planets, but gases that have been expelled from the external shell, they start forming again younger stars, and the cycle will reproduce itself. But this also, leads to the formation of galaxies that are, the composition or the cluster of multiple stars together, surrounding probably a black hole or a neutron star. Final concept that we're going to discuss is the resonance, or final phenomena, if you will. So in nuclear reactions, resonance occurs when the kinetic energy of an incident particle matches that, or the energy level, of an excited state of the compound nucleus. As an example, if a neutron collides with a nucleus and its energy matches an excited state of that nucleus, the probability for a reaction to occur or to take place jumps or peaks up. This is called resonance peak. In particle physics, resonance is an unstable particle that appears as a peak in the cross-section, or sigma, of a scattering process. It remains for a short time before decaying into smaller particles. These resonances are virtual particles or excited states seen in high-energy collisions. We're talking about accelerators such as LHC in CERN. Okay, thank you so much for watching. This is all for this session.